Justin Miller, also called Physics here, and we are going to get electrified. Okay, so we've looked at how a charge that's moving within a magnetic field is subject to a magnetic field force, possibly, depending on the orientation. So what if instead of just a charge, we had, say, a current carrying wire, and we stick that wire in a magnetic field? Well, if it's a current carrying wire, it has charges moving through it, and if those charges are moving perpendicular to the direction of the magnetic field that the wire is immersed within, there's going to be a magnetic field force exerted on the individual charges, which overall is thus exerted on the wire itself. So we have magnetic field force exerted on a current carrying wire. So we can have some current carrying wire. Let's just say we've got some current like this, and we'll just look at this one little section here. And we have some magnetic field that this wire is immersed within. Place that wire in this magnetic field. The charges that constitute the current interact with the magnetic field and have, voila, that's it. They got a magnetic field force exerted on them. So if they are positive charges going this way, the direction of the conventional current, we can still do ourselves in terms of directions as charges are moving this way. Direction of the magnetic field is the palm, which is into the board, and the force would then be upward. So all across this current carrying wire, we'd have this force distributed across it. F sub B hat due to the charges moving through B hat. It is. We just use the right hand rule. The only difference here is that we're not looking at individual charges. Now, you may say, well, generally current's electrons moving, right? That's right, but they're moving in the opposite direction of the conventional current. So if instead we said, well, actually, this current is electrons moving that way, what would the difference be? So now we've got charges moving this way, magnetic field is into the board, and our thumb points down, but these are negative charges that we're considering. So the force on them would be in the opposite direction, which would still be up. So the point with this is that it doesn't matter if we're talking about the conventional current or the electron current, we get the same direction of the force as we should, and that's why we just stick with utilizing conventional current because it's what we're conventionally using. All right, so ultimately, this comes down to another cross-product relationship between the charges, them moving through the magnetic field. And ultimately, we get the magnetic field force on the overall wire. We could say has some length L. Is L multiplied by I hat cross B hat. Sometimes, in some places, like your book, you'll see that they don't use I hat, they use L hat. I prefer I hat, to be honest. The current has a direction, and it's not really the length element that has a direction. Doesn't matter though. Ultimately, we take the direction that the charges are moving, the direction of the current, cross it into the direction of the magnetic field, and we get the interaction, multiply it by the length, and we've got the total force that's distributed across the wire itself. So, what one could do with this is define the force per unit length. F sub B hat divided by L is the force per unit length. distributed across the wire. And we can write then that f hat sub b divided by L is then equal to I hat cross B hat. It's pretty much that. We just wanted to talk about the magnitude. The magnitude of the force per unit length is just going to be IB times the sine of theta. And then we can use the right-hand rule to determine the directionality, or use cross-product relationships to determine the directionality of the subsequent force itself. So, right-hand rule regarding this system. Fingers, current, palm, magnetic field, and thumb is then the force. So it's basically the same thing that we had. We're just replacing the direction that the charge is moving with the current. That is the direction they're moving though. So there's how we subsequently utilize the cross-product rule. And what's new? Nothing much. It's still kind of the same scenario, except we can do a couple other things with this. That's what we want to look at here. It's not so much just one singular wire immersed in the magnetic field, but what happens if we have sort of an extension? If we have, say, like a current loop that's immersed within a magnetic field. So that's what we want to focus our attention on really quick here. I should say really quick because it's really not that quick. But now consider a current loop in a magnetic field. I'm going to make it into like a rectangular loop. That's fine. Hopefully that's fine with you. We're going to go ahead and say something like this. We'll say it has some dimensions here. We'll say that this is dimension B. There's a dimension A. And we'll say that we have the current cycling around here, not drawing in a source potential, but there has to be something driving the current. But here is our current going around in a clockwise manner here, conventional current. All right, and then we're going to take this, we're going to immerse it within a uniform magnetic field. So I'm just going to take some outside field here. I'm going to say that it's into the board. Equals uniform. All right, so we immerse this current loop within this uniform magnetic field, and we say, is there a net force exerted on this current loop? So what we're going to do is look section by section, and we'll say that this is number 1, this section is number 2, this section is number 3, and this section is number 4. So we got 4 different segments of a current that are going to interact with the magnetic field. We want to look at all 4 of them. So we want to look at the net force on the loop. All right, so we're going to say we've got ourselves some F hat 1. And this is the magnetic field force on segment number 1. What's that going to be equal to? Well, that is going to be equal to IB times the sine of theta 1. It's the same current in the same magnetic field everywhere, so no need to make a distinction there. And then it has a direction too. We'll get the direction here momentarily. And we ask ourselves, what is theta going to be? Well, if the direction of the current's up, the direction of the magnetic field's in, theta is going to be equal to 90 degrees. So theta 1 is equal to 90 degrees. So really, F hat 1 is just equal to, excuse me, we need an L here too. Excuse me, a B, because there's the length. So we get an I, B, B. there's the magnitude of the force right there. We also need the direction. So it's the current times the magnetic field times the length of the segment gives us the overall force on the segment. And fingers go up, palm into the board. We got the force would be outward. So let's just use right here. So we got across this length here, we got this force F1 hat distributed all across it. Great, and there's its magnitude. We come over here to segment number 2. So this was for number 1. Now we do number 2. And again, we're going to have, now the current's going to the right, magnetic field's into the board. There's a 90-degree angle in between them. The length of the segment's going to be A. And we got then that F hat 2 is going to be equal to I times B times A. Again, theta is going to be 90 degrees, so we just leave that out. And we put left there. And we say, what's the direction of the force? Well, I crossed into B gives us F. So the force direction, which we could call F2 hat, is up. Proceeding onward, we go over to number 3. Current's going down. Magnetic field's in the board, still a 90-degree angle in between them. We got this segment that has a length B, and we've got ourselves then that F hat 3 is going to be equal to IB times B. And what direction is that going to be? Current's down, magnetic field's into the board. We've got ourselves the direction of the force would be to the right. And this is F hat 3, and then we got F hat 4. So this is right, and then number 4, F hat 4 is equal to the length of the segment A. We've got the angle between the current and the magnetic field is still equal to 90 degrees. Got the current multiplied by the magnetic field strength, multiplied by the the segment length. And then we say, what direction is that going to be? Current, magnetic field, force is downward. So there we got the individual forces here on each segment. What do? Well, if we want the net force, we just add them all up, right? So the net force on the loop would be equal to F1 plus F2 plus F3 plus F4. What's that going to be equal to? Well, look at this. F1 and F3 have the same magnitude, opposite directions. They cancel each other out. F2 and F4 have the same magnitude, opposite directions. They cancel each other out. So net force is equal to 0. If this is rigid, nothing happens. If there's some elasticity in these wires here, they likely bow outwards a little bit, but that would just be a matter of how much elasticity and when does the overall net force structurally equal 0 or balance out with this magnetic field force. Overall, the net force is 0. It's not like it starts moving around or anything. Say, wow, that's impressive. Nothing happens. Yeah, that is impressive, huh? Not really, not really. Because we want something to happen. We want something to happen. So the question becomes, is there some way that we could make something happen, make something move? And, well, let's try a different orientation of the magnetic field with respect to the plane of the loop. I'm going to take this loop and I'm going to rotate it like this. I'm going to rotate it by 90 degrees, but ultimately I'm going to draw it out a little bit different. So that if I rotate it by 90 degrees, we would have that the magnetic field now is moving this way. It depends which way I rotate it 90. It doesn't really matter, but this is what we're going to do now. So, let's consider another orientation. So consider this. take ourselves our loop here. So the current's still going around. That's a great. We've got, there's our eye, still going clockwise. But in essence, I am going to rotate the magnetic field by 90 degrees. So it was pointing into the board. I'm going to make it point that way. So now I'm going to say, okay, we've got a uniform magnetic field that's going like this. The question is, does anything happen now? Well, we got to go see again, right? We've got these 4 segments. We could still utilize that. We got number 1, number 2, number 3, number 4. We're still saying that this is B by A, B by A. We just look at each segment. So let's start with segment number 1. Let's look at the orientation of the magnetic field with respect to the direction of the current. Current's up, magnetic field's that way. There's a 90-degree angle in between them. So if we look at the force, F1 hat, that is going to be equal to the current multiplied by the magnetic field strength multiplied by the current segment length times the sine of 90 degrees, which just gives us the same thing. We've got the same magnitude of the force. What about the direction? Let's see. Current's going up, magnetic field's that way, and the force would be into the board in this case. So we've got the same magnitude of a force that we had before, just a different direction. All right, then let's look at segment number 2. What's the angle between the direction of the current in segment number 2 and the direction of the magnetic field? That's it. 0 degrees. Sine of 0 is equal to 0. So F2 hat is equal to 0. There is no magnetic field force because the direction of the current's in line with the direction of the magnetic field. Okay, so we skip on over that. That's different than what we had last time. Come over to this one. 90-degree angle in between the direction of the current and the direction of the magnetic field. Good. We've got ourselves an F3 hat is going to be equal to I times B times the current segment length, which was B. And then we say, well, what is going to be the direction? Now we've got the current going down. We've got the magnetic field to the right. I've got that the force on it is outward. So on this side, outward. All right, and then we can come on over to number 4. And what's the angle between those two? The current versus the magnetic field, 180 degrees. That's right. So we've got ourselves theta 4 is equal to 180 degrees, and thus F hat 4 is equal to 0. So if we look at the net force again on the loop, well, 0 and 0, 0. This and this are the same magnitudes, opposite directions. So what do we have? Yeah, the net force is still equal to 0. F1 hat plus F3 hat is equal to 0. Oh man, that seems boring again, except it's not boring because we got something else going on here. What happens if you take something, maybe not square, but you just take something and you exert a force on one end of it that way and a force on this end of it, the opposite side of it, the opposite way. So if I push outward on this side and pull inward on this side, what happens? Oh man, it rotates, that's right. It rotates. Whoa. What's happening here? These forces are constituting a torque on this current loop and producing a rotation. All right, once it's rotated into this orientation, however, then we've got this going on again. We got the magnetic field is going through the plane and all the forces are outward everywhere, and we've got the net forces equal to 0, no more torques. All of those forces are radial, none of them are tangential. So this is what happens. We get that this force is always directed inward, this force is always directed outward, and it just becomes that eventually it goes from here, I'm kind of doing this wrong, inward, outward, there we go. It goes from here, I'm mixing myself up, twisting things. What does it say? It goes from here to here, and then kind of locks up into this position. Now, we may be able to get that its momentum carries it through this, but the force on this side is going to be out, the force on this side is going to be in, and it's just going to want to lock back up into here eventually. Maybe it wiggles back and forth a little, like this. So what can we do with this? Well, if we started it way over here like this, we could get it to spin about halfway around. But then again, it wants to lock up after half of a rotation. We want to keep it rotating. How are we going to do that? Well, we'd have to have some way of either changing the direction of the magnetic field after half of a rotation, instead of having it this way, have it go that way, or change the direction of the current after half of a rotation. And well, both are possible. One's a little bit easier to pull off, but this starts to be the essence of how electric motors work. Electric motors are all around us. You go to the grocery store, the door opens up, right? There's a little sensor that senses you there, and then whoop, these little electric motors open the door. You don't see them, but they're there. There's something moving around that moves some gears that open the doors. There it is. You roll up your window, roll down your window in the car, assuming you don't have the handles. That's an electric motor doing it. You're driving your Tesla, you got yourself an electric motor. I wish. Anyways, that being said, electric motors are everywhere. Everywhere, but there are lots of places. And this is a principle by which they work. It's as simple as a current loop that's immersed within a magnetic field. You can start getting things more complex, but ultimately, bare bones, that's all it is. This is a little electric motor here. It's got some external magnets. These little magnets here. And it's got this current loop right here that's kind of housed on a nice little axle, and then it's got some little brushes that I can connect to a power supply, which I'll do right now. Got myself a little battery right here, and I'll plug this side in, and go ahead and get those going. Give it a little, get it going, spin. This is what we've got going on. Spins around. Now, it spins around because of the magnetic field of these external magnets here interacting with this current loop. And there's something in here that's allowing the direction of the current to switch every half of a rotation, so we get this sustained torque directionally, which keeps this spinning. That's a little bit more complicated. We'll get to that at another point. But ultimately, again, it's just an interaction between an external magnetic field and the current itself, producing forces which correlate with a torque. I move the magnets far away, or actually I take the magnets off. What happens? It stops. It stops because if there's no external magnetic field, there's no force. And if there's no force, there's no torque. If there's no torque, there's no rotation. And now I got these magnets stuck together. I put the magnets back. Put one back. Usually one will get a little bit of rotation, but I get the other one there. And it gets even stronger. I push the magnets even closer to the loop. The magnetic field force is stronger and it spins faster. I move them far away from the loop and it slows down. Not a whole bunch, but I take them all the way off, it stops. I unplug it. Hey, there's no more current. Eventually, this will slow down and stop. Stopping and stopping. No more current, no more interaction between the magnetic field that's still there, but no more moving charges. I need the moving charges in order to substantiate the torque on that loop. All right, cool enough. So I'm going to go ahead and disconnect that. This, and what we want to do is be able to quantify this torque here. So, yeah, let's do that. One sec. All right, so we just got to go ahead and say this. We'll assume that this has a nice mass distribution that's even, so that it would want to rotate about its center, or we could even just go so far as to say, we'll just put it like an axle right here. Hinge this whole loop to a nice axle so that we've got that this object, this will tend to undergo some rotation like that. At least when it's in this orientation, it wants to rotate out like this. So we want to know what's the torque and how does it vary and all that stuff. So here's the axis of rotation. Basically this line right here. And what are we going to have? Well, we're going to have that this edge here is some radial distance away from the axis of rotation, and this edge here is some radial distance away from the axis of rotation, which both happen to be a distance of a over 2. So the magnitude of the radial distance from the axis of rotation is going to be a over 2. And then we've got ourselves the torque itself. Torque is R hat cross F hat. So we've got two different torques here. We've got a torque on this side, tangential force acting at some radial distance away from the axis of rotation, and a torque on this side. So let us check these out one by one. We'll call this side kind of a tau 1, which would tend to produce kind of an inward rotation on this side. This side wants to go into the board. Here's our tau 1. Tau 1 is going to have a magnitude, let's just do the whole thing. Tau 1 is going to be equal to RF times the sine of theta 1. And what direction is that going to be in? Well, if we say R cross F, in this particular case, R's this way, F's this way, the torque on this side is actually downward. But that downward torque directionally is correlated with this rotation that would push this side into the board. So true direction is down, that's fine. Anyways, it's hard to say clockwise or counterclockwise at this point unless we agree that we're going to look downward on this or we're going to look upward. If we're looking down, this would be a clockwise rotation. If we're looking up from underneath it, it would be a counterclockwise rotation. Let's just say it is directed downward. So we know what F1 is, and we know what R is. So you got that tau 1 is equal to A over 2 times F1, which is IBB, times the sine of theta 1. We'll come back to this. Right now, this orientation, theta is equal to 90 degrees. But as it starts to rotate, that angle starts to change. Again, this is the angle between the radial vector and the force vector. Right now, the force is completely tangential. As it starts to rotate, the force continues to be inward, but the alignment of R hat is no longer perpendicular, completely perpendicular to it. Anyways, we've got that, and then we've got ourselves that tau 2 is going to be equal then to R times F2 times the sine of theta 2, and that's going to be directed upward. And let me put down there. How do I know that that's, nope, it's not up, sorry. What direction is this torque? Gotta slow down sometimes. Take a breath. Now we've got R this way crossed into F, which is out of the board. The torque directionally is downward. Ultimately, the two torques are in the same direction, which then have the tendency of producing the same directionality regarding the rotation. That's what the important thing is. This is down as well. And we've got then tau 2 is going to be A over 2 times I times B times the sine of theta 2 downward. As this rotates, the orientation between R and F is preserved on each side. So theta 1 is equal to theta 2 is equal to theta, we'll just call it, at all times. because it's rigid, this side rotates by the same amount that this side rotates, and we got the same orientation, again, with respect to the axis, the radial vector and the directions of the forces. So, if we want the net torque, what are we going to do? Well, we're going to note that the two torques under consideration are on the same side, and I was calling this 2. Technically, we should call it 3 here, F3. Say that there is some tau 3 over on this side. Little badness. All right, kind of fix that up. 3. And then we've got ourselves the net torque would be equal to tau hat 1 plus tau hat 3. Both are in the same direction, downward, so we can add up their magnitudes, say the overall torque's downward, and we've got ourselves A over 2 IBB sine theta plus A over 2 IBB sine theta, which is then going to be equal to AIB B sine theta downward. There is the overall net torque, and it's even written in terms of theta. So, how do we want to interpret theta here? Well, in this orientation, we want theta to be 90 degrees. Direction of the force, direction of the radial vector, 90 degrees. But as it rotates, the radial vector lines up with the direction of the force. So the radial vector is like this, it rotates, and it aligns with the force on that side. Same with on this side. It's the same thing in terms of alignment. So it starts at 90 in this orientation, moves over to this, at which time the direction of the force and the radial vector, they're in the same directions on either side. No more torque. So what is typically done here is we call this theta the angle between the normal of the plane of the loop itself and the direction of the magnetic field. It's a little bit easier to discuss. So theta can be represented here as angle between the normal of the plane of the loop and the magnetic field. So we've got this going on here. Magnetic fields like this. We've got the normal of the plane of the loop, we could say sticks out like this, or is inward like this. That doesn't really matter. It does a little bit, but it's okay. So I'm going to go ahead and just say it's like this on the back side, sticking straight out, perpendicular to the plane here. And what happens? Right now it's 90 degrees. Direction of the magnetic field's that way, and then there's a net torque. 90 degrees, we got a maximum amount of torque, IBAB. And then what happens? It starts rotating. It starts rotating, the angle between the normal vector and the direction of the magnetic field starts to decrease and approach 0, which means that this is dropping down. As this gets larger, as this gets smaller and approaches 0, we get that the whole overall term here gets smaller until they're aligned. The direction of the normal vector is equal to the direction of the magnetic field. We've got the net torque is equal to 0. Theta is equal to 0 degrees. Net torque is equal to 0. And that's it. There's this variation along the way. So there's the maximum, and then it starts to get smaller until the net torque right here is equal to 0. And then again, we're in this orientation. Magnetic field is perpendicular to the plane of the loop, aligned with the normal of the plane of the loop. So, after all said and done, you can notice something about this. We got the current, we got the magnetic field, then we got the dimensions of this loop itself, A and B. Then we got the sine theta going on there that has to do with orientation. Well, it turns out that we can rewrite this slightly a different form and say, in general, we can write that the net torque, in terms of its magnitude, for a current loop immersed within a magnetic field is equal to I, B, A, N times the sine of theta. I is the current, B is the magnetic field, that's great. A is the area. Enclosed by the loop. A little bit harder to show this, kind of got to take my word for it, but in this particular case, the area enclosed by the loop is A times B. There it is right there, A times B. But it doesn't necessarily have to be a rectangular or square loop. It could be circular. As long as we know what the area of the loop was, we can go ahead and utilize that. N is the number of turns in the loop. For every successive turn, that is, we can have a bunch of wire wrapped around, we get a multiplication factor. We got another interaction between the current and the magnetic field. So this N is a multiplicative factor that depends on how many turns you have. More turns, greater amount of force of interaction, greater amount of torque. Does that necessarily mean that more is better? And that has to do with, well, how massive is this going to get? If it gets too massive, its moment of inertia gets very large, and you get that the angular acceleration that's produced is very small. Kind of get a trade-off in a sense. So what's optimized this thing is it really depends what you want to do. You want it to be zipping really quick. You want a low moment of inertia though. You want it to take its time and get going. High moment of inertia is fine. But there's kind of a happy medium balance act that depends on exactly the composition of everything in terms of how it's laid out spatially and axis of rotation and any friction and all sorts of stuff like that. But at any rate, this is what we got here. And again, this is sort of the premise by which electric motors work. And I'm gonna leave it at that right now and go from there. All right, everybody, have a good day. It's been a pleasure. Turning the screws with some more torque. Who doesn't love torque? That's what I thought. Take care.